For this part, we build on the definition of logarithm and the basic rules to develop more rules for logarithm. Now, what do we have so far? We have our dictionary to go between exponential equations and logarithmic equations. We have 4 rules. We have log to a base of the base itself is 1, log to the base of 1 is 0, and we have 2 cancellation laws. The 4 rules we develop in this section, the first 3 are going to be analogs to rules for exponents. Okay, remember, logarithm is supposed to somehow represent exponent, so we'll have exponent rules coming in. And then the 4th one is actually another exponent rule, but more importantly, this one is going to let us use technology to calculate logarithms in specific cases with actual numbers. Now, first one, we have the product rule. So this is the analog of the product rule for exponents. We have log to the base b of x times y. What should that do? When we multiply items with the same base, we add their exponents. So we're going to get log to the base b of x plus log to the base b of y. Now, what this says, if we multiply on the inside with logarithm, we add on the outside. Also note there's no corresponding rule for adding on the inside. On the inside, you can only multiply, divide, or raise to a power. Now, how do we show this? This is just language and bookkeeping. If I set x equal to b to the m, y equal to b to the n, I multiply xy by the product rule for exponents. We just add the exponents. We get b to the m plus n. We use our dictionary to rewrite as logarithms. So we're doing the base answer exponent. This is going to go to log the base b of x. The answer is equal to m, the exponent. Log the base b of y is n. Log the base b of x times y is m plus n. And now to get the rule, we just match through m and n. For a simple example, not a lot of numerical work, just symbol pushing. Let's try log the base 2 of 55. Now 55 is 5 times 11. We're multiplying on the inside, so I'll add on the outside, which will give log the base 2 of 5 plus log the base 2 of 11. If we want to go further numerically, I would need my 4th rule in my list over here. Next, let's try log of 10x. Okay, recall, if the base isn't listed, we assume that it's a 10. So I'm really looking at log to the base 10 of 10x. The product rule says I could take the 10x, rewrite as a sum on the outside. So I'll have log to the base 10 of 10 plus log to the base 10 of x. Then log to the base 10 of 10, because we're taking the log of the base, that's just going to go to a 1. So we're looking at 1 plus log of x, suppressing the 10. In the other direction, let's try log to the base 8 of 2 plus log to the base 8 of 32. We'll do the product rule in the other direction. Because we have matching bases, so these 8s have to match, I'm allowed to put this together on the inside by multiplying. So I get log to the base 8 of 2 times 32, or 64. 64 is 8 squared. So we can use our cancellation rule. Okay, the 8s and the log will go away, leaving us with exponent 2. And then just remember what happened here. Well, if the log is an exponent, if I put that exponent over an 8, I'm supposed to get 8 squared, so this exponent is going to be a 2. Now, next rule, we have the power rule. So remember, if I have b to the m to the nth power, what do? Well, we'll just take b to the m times n. So it's like we lose the parentheses. This says if we have log to the base b of x to the rth power, what I'll do is just take the r and move it out in front of the logarithm. Now, to show this, it's the same as we did with the product rule. I'll just let x be equal to b to the m. I rewrite that as log to the base b of x equal to m. I now look at x to the rth power. Well, what are we going to do? I'm going to take b to the m to the rth power, Power rule for exponents just says throw away your parentheses and multiply m times r. We rewrite as a logarithm. Okay, so we have log to the base b. The answer is x to the r. The new exponent is m times r. And then to get the rule, we're just going to sub out the m with log base b of x. And then that's our rule. First application. Let's show the cancellation law just using this and the log rule for log the b of b itself. So what do? If I have log the base b of b to the e, well, power rule says we can take the e, put it out in front. Then I have log the base b of b itself. Okay, so that's going to go to a 1. And then now I just have the e. Things canceled, left us with the e as expected. Next example, let's try log of cube root of x. Here, there's no base listed, so that's a 10, but we're not going to use it, so we won't put it back in. Now, I can write cube root of x as x to the 1/3, so we have log of x to the 1/3. By the power rule, the 1/3 comes out in front. Then we're left with 1/3 log of x, and then that's our answer. We can't take that any further. Let's try one with natural log. Suppose we have natural log of 1 over e cubed. Some things to remember. Natural log is just log to the base e. E is a special number. It's roughly 2.7, but it goes on forever. And that really becomes more of a thing when you get to calculus. But for now, special number shows up everywhere in science. What can we do? Well, for the first line, I'm going to rewrite natural log as log of the base e. The 1 over e cubed we can write as e to the minus 3. I could use the power rule to bring the minus 3 out in front. We have log to the base e of e. They cancel to give me a 1, and we wind up with a minus 3. You'll note we really could have cleaned this up in the second step using the cancellation law. Okay, we saw it on the previous board. The e's are going to go away, leaving me with a minus 3. Now, next level up, we want to start combining rules. So here we're going to combine product rule with the power rule. First thing we have, let's take log of x cubed times y to the 4. Again, base 10, but we're not going to need it, so I'll just leave it off. What can we do? We have a product on the inside, so we can write that as a sum of logs. So we'll get log of x cubed plus log of y to the 4. Now, for the terms on the inside, I can apply the power rule. The 3 can come out in front, the 4 can come out in front, so we get 3 log x plus 4 log y. So that reduces this complicated expression to something that I can compute a little bit easier. Okay, we're not taking powers of things if I know how to get log of x and log of y. Or we can go in the other direction. I could start with a combination of logs, so like we can add, subtract, multiply by numbers out in front. If we're going to use the product rule, though, a few things that have to be in place first. The bases on the logs all have to be the same. So note here, we'll have a 2 and 2. I can't have numbers out in front, but we can get those on the inside using the power rule. And then the plus in the middle, we're allowed to put things together. So let's take a look. We've got 3 log the base 2 of 3 minus 1/2 log the base 2 of 81. We have the same base, log 2. I want to put this together. We got to clean things up first, though. So the 3 comes to the inside to get rid of the 3 in front. That goes to 3 cubed. That goes on the 3. Then the 1/2 is actually a minus 1/2. I'm going to take that minus 1/2 and bring it onto the inside, so we'll have an 81 to the minus 1/2. That's going to give me, so we'll have a log base 2 of 3 cubed, or log base 2 of 27, plus log base 2 of 81 to the minus 1/2. What do we do with negative exponents? Well, we're going to draw a bar in over a 1, and then we're just going to cross the bar to lose the minus sign. So I have 1 over 81 to the 1/2. That's square root of 81, so we get a 1/9. Now, nothing in front, plus in the middle, same base, so we can multiply together on the inside to get log base 2 of 27 over 9, and then that's going to just simplify to log base 2 of 3. Then we need the fourth rule if we want to take this to numbers. Now, in the previous example, I sidestepped one of our other rules, the quotient rule. Depending on how your tastes run, so myself, comfort with negative exponents, I can get the quotient rule in practice just by applying power rule and product rule like in the previous example. Don't need to go to this. Sometimes this is good to have around though. So let's take a look. I have log the base b of x over y. It's equal to log the base b of x minus log the base b of y. The way you should think of this is if we take our exponent rule for a quotient, so b to the m over b to the n, what do we do with the exponents? Well, we're just going to take the difference. So that's consistent with what we do when we think of logarithms as acting like exponents. Now, to see the work, I'm just going to use our product rule and power rule to show this. I've logged the base b of x over y. So I can rewrite that as x times y to the minus 1. Okay, that might be over 1, you cross the bar, but that can move up into the numerator. Product rule says we could take this product, write it as a sum of logs, so we get log the base b of x plus log the base b of y to the minus 1. And then I just bring the minus 1 out in front to get our difference. So that's our rule. Now, a few examples. Let's try log to the base 3 of x over 27. I could write this quotient as a difference of logs, log the base 3 of x minus log the base 3 of 27. We could do some work on the log base 3 of 27. So what's this? 27 is 3 cubed. Cancellation law lets this go to a 3. And we get log the base 3 of x minus 3. I could try one with log. So here it's assumed that we're doing base 10. If I have log of 100 over y, rewrite this with the 10. 100 is 10 squared, and so we're just taking the difference of logs here. Cancellation says log the base 10 of 10 squared. We get a 2. And then minus log 10 of y, I can just rewrite that as a log y. So 2 minus log y. As with the product rule, we can go in the other direction. So if I have a difference of logs, as long as they have the same base, there's no numbers floating around other than the minus, what can we do? I bring them in to the inside, not as a product now, but as a quotient. So if I have log the base 4 of 32 minus log the base 4 of 8, we have log the base 4 of 32 divided by 8. That's going to go to a 4, and then log the base 4 of 4, it's one of our rules, that's going to go to 1. So if you have log of your base on the base itself, you get a 1. Let's try all 3 of our rules now. So we have 2 log x minus 4 log y plus 1/2 log z. Can't use any of our rules if there are numbers out in front, so we move them all to the inside as exponents. Log x squared minus log y to the 4 plus log z to the 1/2. Now, I could put these all in at once. The pluses go in the numerator, the minuses go in the denominator, or you could do them, pairwise and just keep adding one more into either the numerator or denominator, depending on whether plus or minus. So what would happen? X squared goes to the numerator. The z to the 1/2 goes to the numerator. We can make it square root of z. And then minus log y to the 4 is going to go in the denominator as a y to the 4. And then we wind up with this expression here, everything inside of a single log. For our last rule, this is the rule that lets us do numerical work. So this is what we call change of base. And for us, we're just going to do change of base so that we can get to the calculator. Now, what we have is, if I take log to the base b of x, and let's suppose we want to get numbers, what do? I have an option. I could either use the log key on my calculator, and then I would go for log of x divided by log of b, or I could use the natural log, the ln function on the calculator, and it's the same pattern, natural log of x over natural log of b. Let's first do an example just to see how the numbers fit together. So, why don't we go with log to the base 5 of 90. If I use the base 10, the log button, we'll get log of 90 over log of 5. Put those in the calculator, I get, going out to like 5 decimal places, 1.95424 over 0.69897. That gives me a 2.796. Now, those are just numbers. What do they mean? Remember, the answer that comes out of logarithm is an exponent. I put that over the base, I get the answer, the thing inside the parentheses. So you could check, if I take 5 raised to the 2.796, that's going to come out in the ballpark of 90. Did I have to use log here? No, I'll get the same exact answer if I use natural log. So if I took natural log of 90 over natural log of 5, different numbers. I have 4.4998 over 1.60944. What comes out, at least rounding to 3 decimal places, 2.796 again. So we have options here. Now, where does this rule come from? First, let's note, there's nothing special about base 10 or base E here, other than it works with the calculator. If I want to go base A, the pattern's exactly the same on the right-hand side. It would be log AX over log AB. We'll just show this for log with base 10. Now, what are we going to do? First, although we're using the rules of quotient, I'm going to clear the denominator so that I'm really working with the statement log to the base b of x is equal to log, and now I'm doing base 10, so I'll put it in there. Log to the base 10 of b, I want to know, is that equal to log to the base 10 of x? So that's just our rule in multiplied form. Now, proof, really cheap. All I'm going to do is use our power rule. I'm going to take all of log to the base b over x and move it to the inside. That's going to give me log to the base 10, and then on the inside I have b to the log to the base b of x. That's our cancellation law. The b's match, so the b's go away, the log goes away, and I'm left with an x, which gives me log to the base 10 of x, which is what we were hoping to get on the other side. So that's one of our cancellation laws. Now, let's return to the original problem. We pose this as a money problem, but what we're really doing, I want to know for what t does 2 to the t equal 1,000. If you recall, the model for this was at time 0, we have $1. As I go from day to day, we're just going to multiply the amount we have by 2. So we'll go from 1 to 2 to 4 to 8 to 16. I want to know when we're going to clear 1,000. We saw it only takes 10 days to go over 1,000. Let's do it using logarithms. So if I have 2 to the t equal to 1,000, okay, remember we have base, answer, exponent. I put it in logarithmic form. The exponent is a t. Okay, so that's going to be what we're looking for. Our base is 2. Our answer is 1,000. Now, log the base 2 of 1,000. I don't have keys for that on my calculator, so I got to switch to say base 10 or natural log. We'll just use base 10. I have log of 1,000 over log 2 using our formula. These I could put in the calculator, which will give a 3 over a 0.3010. We simplify and we get 9.965, which means if this rule worked for all times t, so including fractional t, you would cross 1,000 at the end of the 9th day. But since we're assuming, let's say it doubles when we check in at 8 o'clock in the morning, it'll take 10 days for you to get over 1,000. You just got to get past this number here.